Okay. Let me try one thing. Okay, it seems like we can go on now. Perhaps, Stoyan, I think you have to say it again. I'm not sure if people listen to you. Apologies for that.
No problem. So I'm sorry for this glitch in the start, but let us start again now from the Journal Club. It seems that most of the participants have not been able to hear us. So welcome to the second Journal Club in the series organized by Physical Review Journals. The second Journal Club will be presented by Jessie Zhang from Harvard University, and it will be on the article called Forming a Single Molecule by Magnetoassociation in an Optical Tweezer. This research has been published in Physical Review Letters just last week, and there is also a synopsis written by our physics editors. As a panelist, we have a number of co-authors from the same paper, more senior co-authors, so all of your questions that you may have either for Jessie or for the panelists will be answered after the talk. We are very happy to welcome our moderator, Cindy Regal from Jila in Colorado. And after I finish with this short presentation, Cindy will take over and moderate the rest of the session. So before we start, just a little bit of info on our GoToWebinar panel or platform that we are using for this seminar. After the talk finishes in about 20 minutes time, all of the attendees will be made to be presenters. This will allow all of you to video chat in this Journal Club as it is attended. Sometimes it may be needed for a video to be enabled that people restart either the GoToWebinar program or the whole computer together. Now, we don't want you to lose any time from the talk or the question time. So if this is the case, you will be able to either ask the question verbally just without your picture present, or to type it in a chat. Speaking of that, we would prefer everyone who has a question to type their questions in the chat window first. In that way, the moderator will be able to select the questions to present to the author. Then the moderator will address individual questionnaires and unmute them so they can either ask the question through our system, or she will read the question to the author altogether. So I hope this clarifies it for the platform a little bit. Changing the topic, we are very happy to announce that we have started receiving submissions for our new journal, PRX Quantum, just later last month. The journal is intended to serve as a journal for the entire quantum information science and technologies communities. In that way, it will spread outside of the boundaries that were currently published in physical review journals, and will invite papers on the more computer science and mathematical side on one side, and in the other extreme, more on the engineering side, with the device engineering and optimization and so on. So we hope that this new journal will be a home for the computer science, quantum information science and technology community. Another good news about this journal is, of course, that APS is willing to waive all of the author publication charges until 2022. With that, I will switch back to Cindy, and I will ask Cindy to start moderating the session and introduce our today's speaker.
Great, thank you, Stojan, and thanks to APS Journals for putting together this engaging series. As you said, I'm Cindy Regal. I am at Jila and the University of Colorado. And today we have as our speaker, Jessie Zhang. So she received her undergraduate degree at MIT, and she joined the NE group at Harvard in 2015. The NE group is in the chemistry department at Harvard and works in ultra-cold molecular physics and chemistry. And Jessie will tell us about recent work creating a single, very weakly bound, but also stable molecule in an optical tweezer. So in case you missed the instructions at the beginning, let me reiterate a little bit about how the timing will go today. So we'll have a 20-minute talk from Jessie. So at this point, that'll go until a little after 9:30. And the default is to try to go through the entire talk without interruptions, and then we'll have plenty of time for questions after, sort of 30 to 40 minutes. As Sojin said, you should put your questions in the chat part of feature of GoToWebinar and not the questions part. Also within the chat, if there are technical issues as we go along, like you can't hear or something isn't working about the connection, feel free to put that in the chat as well. As I said, we'll try to go through without interruptions, but if you have questions as we go along, feel free to write them in the chat, and I'll try to start sorting through things so we can get to the questions right after. So with that, I think I'll pass it over to Jessie and we'll get started.
I think I need presenters. Yeah. Okay.
Yep, you have it.
Okay. Hi. So yeah, thank you, Cindy, for the introduction. And also thanks to APS Journals for putting together this series of events and giving me and my co-authors this opportunity to present our recently published results to you all. So I'll be talking about our recent results in forming a single molecule by magnetoassociation in an optical tweezer. And all these underlined are here with me on the panel today. So first, I would like to give a big picture of what we're after. In the realm of quantum science, a big experimental goal these days is to create a quantum system that is simultaneously scalable, fully controllable, meaning that we can control all its degrees of freedom, and capable of generating entangling interactions. And so many such platforms already exist or are being actively developed. And each platform has their own features that make them suitable for various different applications. And indeed, many of these platforms have already seen wide utility in a lot of quantum computing and quantum simulation applications. And we would like to add molecules in optical tweezer arrays to the picture. And you may wonder, with all these platforms existing already, what do we think putting molecules in optical tweezer arrays can add to the picture? Well, to begin with, ultra-cold molecules, compared with their atom counterparts, possess a much richer internal structure. In addition, if in the case of polar molecules, they can also interact with each other via long-range dipole-dipole interactions, which is also highly tunable. And these features lend itself useful to a lot of applications in quantum sciences. So for example, one can imagine building a quantum computer out of ultra-cold molecules where each molecule acts as a qubit, and the information is stored within the internal states of these molecules. And gates could be achieved by using this long-range dipole-dipole interaction. Now, a key ingredient for a lot of these proposals is the ability to address each of these molecules down to the individual particle level. And that's where we think that optical tweezers can offer their unique advantages. So in particular, with particles trapped in optical tweezers, it readily provides single-site imaging and addressing, and also provides very good single particle control. So for example, pioneering work done in Cindy's group at Jila, they were able to entangle two atoms by carefully preparing their external and internal states and bring them very close together. And more recently, many groups around the world have shown how these tweezer arrays can be scaled up to very large systems and with configurable geometries. So we envision that the single particle control enabled by optical tweezers can allow us to utilize these features of ultra-cold molecules to its fullest. So if we were to go back to this list of features one desires in a quantum system, we see that indeed it would readily generate entangling interactions and would also be scalable due to the optical tweezers. However, while single particle control has been demonstrated really well for atoms in optical tweezers, it's not immediately generalizable to molecules in optical tweezers. And so that's where our work comes in. And I hope that by the end of this talk, I will have convinced you that we can turn this bullet point also into a check mark, at least for a single molecule in an optical tweezer. So how can we go about controlling all the degrees of freedom of a single molecule in an optical tweezer? Well, we first need to consider all the degrees of freedom there are. So in particular for a molecule, it consists of internal states, including electronic, vibrational, rotational, and hyperfine degrees of freedom, as well as external states that is provided by the external tweezer confinement. And so one natural way to think about controlling these molecules is to trap single molecules in optical tweezers and doing all the state purification on the molecules themselves in these optical tweezers. And indeed, the Doyle group at Harvard has recently achieved great success on this front, where they were able to trap arrays of calcium fluoride molecules with optical tweezers. However, challenges still remain in terms of fully taming all the degrees of freedom of a molecule, especially the external degrees of freedom, simply due to the great complexity of these molecules. So an alternative approach and somewhat complementary approach would be to think about the degrees of freedom that each of the constituent atoms in a molecule possess in an optical tweezer. And as in the case with molecules, atoms also possess internal and external degrees of freedom. However, a key difference here is that we know these really well, and we know how to control these really well. And therefore, one could imagine another approach where instead of starting from molecules, we start from single atoms and do all the state preparation on the atoms before converting them to molecules. And so if there's a way for us to convert the molecules in a way that doesn't add extra entropy to the very pure state we start in, we would end up with a molecular state with very low entropy as well. So the question becomes, how do we control the molecular state through our very fine control of the atoms? And so this will be what I will be talking about for the rest of the talk. So fortunately for us, nature has given us means of doing so. And one particular method that is a well-established technique is that of magnetoassociation. And magnetoassociation is a method where one can convert atoms into bound molecules by ramping a magnetic field. And a crucial point about this process is that it is adiabatic, meaning that there's no additional entropy added to the system in this process. Therefore, one could convert from atoms to molecules and back into atoms without destroying the quantum states. Now, magnetoassociation is made possible by a phenomenon known as Feshbach resonances. And so very briefly, Feshbach resonances is a kind of scattering resonance that occurs when the energy of an atom pair coincides with the energy of a molecular bound state that is supported by some other potential. And near this resonance, these two states couple strongly and one gets a scattering resonance. And one point I would like to make here that will become relevant is depending on the relative angular momentum these atoms possess, these Feshbach resonances can be characterized into, for example, S wave, meaning no angular momentum, or P wave resonances, which is the case where the atom pair has a single quantum of angular momentum. And I should mention that this method of magnetoassociation, it has been demonstrated in a wide variety of systems throughout the world. And we follow their approach and adapt it to optical tweezers and find that optical tweezers offers very unique advantages. So why do we think magnetoassociation is good for full quantum state control of a single molecule in an optical tweezer? To answer that question, it helps to think about how the process converts between the different degrees of freedom of an atom pair and a molecule. So in particular, if we think about the motional states of a single atom pair in an optical tweezer, under certain approximations, it can be separated into the center of mass degree of freedom, which is the movement inside the trap, as well as a relative degree of motion, which is between the two atoms. And in a tight optical tweezer, both of these are quantized. On the other hand, for a molecule, it also has a center of mass motion, which is its external state, which lives in the optical tweezer. However, the relative motion actually becomes an internal state. So for example, consisting of the rotational and the vibrational degrees of freedom. And what is nice to us about this magnetoassociation process is that there is a nice correspondence between these degrees of freedom. So in particular, the external state of the molecule inherits that of the center of mass of the atom pair, whereas the internal state comes from the relative motion of the atom pair. So to put this more concretely, so for example, if we were to have an S-wave Feshbach resonance, what one could do is to convert absolute ground state atom pairs, so in both their center of mass and relative motional ground state, into a molecule in an external and rotational ground state molecule. On the other hand, if we had a P-wave resonance, one could start in a relative motion excited state with exactly one quantum of relative motion excitation and end up with a molecule that has one quantum of rotation. And this is an internal state of the molecule. So this is showing how by controlling the external states of an atom pair, we can address both the external and internal states of a molecule. So it's telling us how we can achieve control over the internal states and external states of an atom pair and map that onto molecules. So this is our blueprint for how we want to achieve this full quantum state control of a molecule. So how does that work out in real life? In our experiment, we start with sodium and cesium atoms. We choose sodium and cesium because they're both alkalis and we know them really well. And as well, sodium-cesium molecules possess a relatively large dipole moment, which would make them favorable for future applications. And so shown here is an image of a single sodium atom and a single cesium atom placed side by side, where we can image individually. Previously in our lab, we have also shown how we can independently cool both species down to their motional ground states with very high fidelity. And in addition, after they are cooled, we can also merge the two atoms into a single trap without introducing any additional heating. And to provide a glimpse of our experiment, so this is what our apparatus looks like, and everything happens in this glass chamber here. And for the step of magnetoassociation that we would like to do, we have these big magnetic field coils that generate the large magnetic fields. for the Feshbach resonances. So to begin with, we would like to try and form S-wave molecules. And just as a reminder, with S-wave Feshbach resonances, one can go from absolute ground state atoms to external and rotational ground state molecules. And we can do so by ramping a magnetic field. So experimentally, what we do is we load single atoms and then prepare them in their absolute ground state. Then ramp the magnetic field up to some large value, and then we can merge the two atoms into a single trap. And then we do a small magnetic field ramp down. And after that, we can separate the traps and image the atoms again. So if this magnetic field ramp didn't cross any Feshbach resonances, then we wouldn't expect anything to happen and we would recover the atoms. However, if this ramp does cross a Feshbach resonance, then we could form a molecule, and when we tried to image the atoms again, we would see nothing because our imaging process is not sensitive to the molecules. So when we do this in experiment, what we see is, so we start from some large value and ramp down to these various magnetic fields. And indeed, before we hit a resonance, we see no loss of the atoms. But around 864 Gauss, we see a sharp decrease in atom survival. And this simultaneous loss of both atoms tells us that we are hitting a Feshbach resonance and we are forming these S-wave molecules. So once we know we can form these molecules, it's helpful to know how adiabatic this whole process is. And in part because it would govern the conversion efficiency that we can achieve. And in particular, this efficiency is a function of the rate that we ramp at. So the magnetic field ramp needs to be slow enough for this process to be adiabatic. So experimentally, we can vary this magnetic field ramp rate and see how the conversion probability changes. And so that is shown in the purple points here. And we indeed see that we need to be slow enough for us to achieve maximum conversion efficiency. Now, if this process is truly adiabatic, then one could expect, as I mentioned previously, after you form the molecules, you can reverse this whole process and ramp back through the resonance and hope to recover the atoms. And so that's what we do here, shown in the green points here. And indeed, we see over a wide range where we are able to form molecules, we can also bring the molecules back. And so this is nice. This is telling us that we can form these molecules and then bring them back for detection if we wanted to do anything with them. And so the next question is, how do we fare in terms of the external state control of these molecules that we form? And to answer that question, we need to go back to this picture where we know that we have to be in the absolute motional ground state to form a molecule also in its external and rotational ground state. And in particular, the internal state here, like the vibrational, is determined by the relative motional state of the atom pair that we started. And for the molecules that we formed, it is the exact state we go to is governed by the Feshbach resonance itself. So we know that if we form a molecule, the internal state will be pure. However, for the center of mass degree of freedom, the motion of the molecule just inherits that of the atom pair. So in principle, we could start with excited center of mass states and end up with excited molecules. But we can know what state we start in for the atoms really well. In particular, we can do thermometry on the atoms to know exactly the population of the center of mass state for the atom pair. And when we do that, we find roughly 77% in the ground state. And so this is telling us that by knowing the state of our atoms really, really well, we can end up in molecular states with very low entropy. And in this case, an external and rotational ground state molecule. And so the next step would be to see if we can move a step further and also control the internal state. And like I had mentioned previously, we have these P-wave resonances where we can go from an atom pair in an excited relative motional state into a rotational excited state. And so how do we prepare an atom pair with exactly one quantum of relative motional excitation? Now recall that in terms of controlling the atoms, we only address the individual atoms. So the way we can create an excitation on the relative motion of these atoms, we choose to drive a transition on sodium. So we intentionally excite the motion, the radial motion of sodium by one quantum. And the reason we choose to do so on sodium is because if you think about the large mass difference between sodium and cesium, the center of mass of this system is really close to cesium. So if you were to do any excitation on cesium, it would mostly go to the center of mass degree of freedom. Whereas for the lighter atom, sodium, most of that goes into relative motion. So we can do this very precise excitation of one quantum of radial motion using Raman sidebands. So by driving on a resonance like this, we can very carefully prepare one quantum of radial motion excitation, which leads to exactly one quantum of relative motion excitation. So once we have the state prepared, we can do the same as we have with S-wave molecule formation and use a resonance, and as we had before, ramp across this resonance and see if we can see simultaneous loss. And when we do that, indeed, we see a decrease in survival when we ramp across the resonance. And we contrast this with the case where we don't have this intentional excitation and the atoms start out in their absolute ground state. And in that case, we see that there is no clear contrast, meaning we don't form molecules in this process. And so this is really telling us that by our very careful control of the external state of the atom pair, we can end up with different internal states of the molecule. And I should mention that for this created molecule, it is also predominantly in the center of mass motional ground state. And so with that, I would like to conclude. We achieved the control over a single internal and external state of a single molecule in an optical tweezer. And as I mentioned, we do this by mapping our fine control over the single atoms onto molecules using magnetoassociation. And it really demonstrates how the fine control offered by the optical tweezers can be really useful. And the next steps for our experiment is now we have these weakly bound molecules. We would like to perform further internal state transfer to bring them down to their rho vibrational ground state. And we use a process called STIRAP, which would maintain the low entropy of these formed molecules. And after that, we can imagine scaling up to more molecules and ultimately entangling these molecules. And we really see this platform of molecules and optical tweezer arrays as a promising platform for quantum science applications. So with that, I would like to acknowledge all the co-authors on this paper. And yeah, we're happy to take any questions.
Great. Well, thank you very much, Jessie, for the clear talk. And I guess we'll give you some virtual applause to the extent that GoToWebinar allows this. So yeah, we want to move pretty quickly into questions from our attendees to the panel. So let me briefly introduce, so Jessie is a graduate student in Kangquan Yi's group who's presenting this, but we have a whole set of panelists who you can you see here. So we have Yichao Yu, Will Cairncross, Jonathan Hood, Kenneth Long, Louis Picard, and Kangquan Yi, all here to help answer questions about this paper. I think we already have some questions here, and we're going to start with the first question from Mahidi Hassan. And the question is related to correspondence between the molecular state and the atom pair vibrational degrees of freedom. But what we're going to try to do is have this a journal club style format where Mahidi can go ahead and ask the question himself. So let's try to do that. Let's see, so I believe he's being given permission now.
Yeah, can you hear me?
Yes.
Okay, so could you elaborate a little bit on the when you made a correspondence between an atom pair in a trap and a molecule, when you talked about that the relative motion is related to how you make the correspondence? Could you go to the slide?
Right. So
yes, on the left, yes. So how the could you elaborate a little bit how the rotational degrees of freedom is like how you make the connection that the relative motion corresponds to the internal rotational degrees of freedom?
So essentially it is governed by the Feshbach resonance. So the depending on what state is coupled to the incoming state here, that would be the molecular state you end up in. And so that's where this correspondence comes from.
Okay, since I'm allowed to ask, so could you elaborate? I have actually another question. Like, what do you mean by one quantum of relative motion? How do you define like? What is,
yeah,
I'm not from this field, so like maybe it's very common here.
Right. So that's a good question. So usually, if you were to just think about an atom in an optical tweezer, you can think of, so it has like XYZ, it has like 3 axes. But when you think about an atom pair, it's more useful to think about it in terms of the center of mass and relative degree motion.
Yes.
And because it's in an optical tweezer, so both of these motions are still quantized. So you can imagine the relative motion is just still, these atoms are like vibrating with each other. Say in 1D, it's just a vibration. And so, and on top of that, this atom pair is also vibrating in the optical tweezer. And then so that would, one quantum of relative motional excitation would be like that excitation. Does that answer your question?
A little bit. I'll think about it. Thank you very much.
Okay.
Okay.
Or
Thank you.
maybe someone else has a better explanation.
Yeah, we could also maybe move on to, I think maybe the next question we could look at is another one about the motional degrees of freedom, which will also maybe continue to clarify the subject. So Matthew Eager is interested in some information about the thermometry of the center of mass state of the molecule. So maybe we go there and then we can go back to some other different topic question.
Am I unmuted?
Yes, you're good.
Terrific. Yeah, I was just wondering about how you keep from accidentally exciting the atoms when you measure them. Is it just that you do it at the wrong energy scale, or how does that actually work?
Oh, sure. So I didn't go into too much detail of how we do the thermometry, but we use Raman sideband thermometry. And essentially so the thermometry is not done like in situ. So it's a separate measurement where we can know the temperature of these atoms, like just like the occupation number of these atoms. And the way, let's see. So actually to do the thermometry, we actually do heat up the atoms and we see how much we can heat it versus how much we can cool it. And so if it is in the ground state, then we can't cool it anymore and we know that it's cold.
Okay.
Yeah.
Okay, thanks.
Great. Well, let's move on to a slightly different subject then. So Anil Kumar has a question about how the interactions play a role in this problem. So should we turn it over to Anil? Let's see. I don't have a great way of telling who is speaking. Kaditya, do you see this? Or who has the microphone?
Is it working?
Yes, okay, I can hear you now.
Okay, thank you. Yeah, so actually the dipole-dipole interaction, it has a repulsive part after a certain distance. I mean, like it's shown there like a micrometer. So I was just worrying that how the dipole-dipole interaction and the waste of the tweezer, I mean, how do the two are correlated?
Sorry, so do you mean like between the atoms or ultimately between
Yeah.
molecules?
Yeah, between the atoms.
So the atoms don't have any, well, only very, very weak, but no dipole-dipole interactions. Because these are
Okay.
neutral atoms in their ground state.
Okay. Yeah, thank you.
Does that answer your question? Okay. So, yeah.
Okay, great. All right, well, let's keep moving along then. And so Kushal Patel has a question about the imaging of sodium and cesium. So let's turn it over to him. Kushal, can you speak or?
Can you unmute yourself?
If we can't quite hear you yet.
Okay, so maybe we read this question out.
Okay, yeah, great. So he asks, how do you differentiate between sodium and cesium in a single shot image?
So essentially because we know the positions of the tweezers. So, and when we actually do the experiment, we actually don't take single shot of both. But for example, if we were to wanted to take a single shot, we couldn't know just by knowing the, because we know where our tweezers are. So a sodium can only exist in one trap and not the other.
Mm-hmm.
Yeah, so that's actually like a point I didn't make, but so these traps, so the trap that we use to trap sodium can only trap sodium, and the trap that we use to trap cesium only traps cesium.
Mm-hmm. So Kushal, feel free to chime in if we can hear you now, or you can type in the chat if that did or didn't clarify your question. Okay, yeah, if you have follow up later, feel free to type it in. Maybe we'll move on then to Robert Risto, who has a question about atom pairs versus molecules. So Robert, do you want to try to speak here?
Sure, I try. Can you hear me?
Yes, great.
Okay, great. Yeah, this is a bit of a naive question. I know you tried to address this at the beginning, but if there's a one-to-one mapping between the states of a pair of atoms and the molecules, what is it that you actually gain by creating the molecule? Is it more stable, or the state more stable, or what is the advantage?
That's an interesting question. So I would say that there is kind of a one-to-one mapping, but so okay, I guess there are two parts to this question. One is just from the point of view of the molecules that we create. The thing is that there's a one-to-one mapping, but the difference that it is an internal state makes it beneficial. So like, because an internal state is, you can think of it as it's like more stable. And on the other part is that so for this particular molecule that we make right now, we can't make them interact with each other, but ultimately, for example, if we actually create them in their ground state, then we can actually make a quantum computer out of them. But I don't think there's any way we could make a quantum computer out of just an atom pair, or at least haven't thought about it.
Great.
I guess if anyone else has any conquest.
Yeah, very broad question, so maybe a good time to open it up to other panel members about sort of different perspectives on the uses of the molecules.
Yeah, I can speak. So that's a very good question, and I think Jessie basically answered it, but just to make it a bit more concise, is that we want the molecule ultimately has a large dipole moment and allowed then to interact via dipole-dipole interaction. So in that respect, this is an intermediate step for us to pair the atom into a molecule, and then the next step is to bring the molecule to the vibrational ground state such that it has a dipole moment.
Okay, great. All right, yeah, if there are more questions, go ahead and type them in. In the absence of other questions at the moment, I can sort of send the conversation in another direction here. So one question that I had is, you know, one of the goals ultimately is to have a very pure state of the molecule that you get in the end, right? To sort of a process where in the end you know that you have X molecule and it's in a certain internal degree of freedom and a certain external degree of freedom. And there's some efficiency by which you do this right now. With molecules, are there any tricks you can play with post-selection to sort of know that you have certain center of mass or relative motions that you don't have in the atomic case somehow? Are there post-selection tricks you can play in the end?
It's a good question. I would need to think about it, but if anyone else has any ideas.
Will, maybe you can chime in here?
Yeah, let's see. Can you guys hear me?
Yes.
Oh, look, you're a little quiet one.
My mic position is not that good. I was gonna say we're looking into a few possibilities. I mean, perhaps the simplest one, and I don't know if this qualifies as post-selection per se, but you know, an example would be if we prepare the molecules and then do something to essentially blast away the atoms if they fail to form a molecule. That's like, in a way, post-selection, right? Then they will only survive if they form a molecule. We're also looking into other detection techniques, say using proximate Rydberg atoms to the molecules, things like that. But under development, basically.
Yeah, okay. No, that's interesting. I mean, yeah, that's utilizing, you know, different properties of the molecules compared to the atoms that maybe you don't have in certain contexts. Cool. All right, well, yeah, let's get back to, we have more questions from the attendees here, so let's move on to another topic. So I think Matthew Eager is back here with a question about particular choice of atoms for making your molecule. So Matthew, are you available to speak again?
Sure. I was wondering why you picked the alkalis you did. You could get a larger mass difference than the one you picked, and therefore in the resulting molecule, a larger dipole moment between molecules, I guess. Are there practical concerns? Does polarizability matter? Does absolute mass matter here? What makes you pick sodium and cesium?
I guess, I don't know, someone else could answer that question. Just Ital or Kenneth, or just to speak.
Yeah, I can speak, I guess. Well, I guess, first of all, we want to use bialkali because alkalis are the easiest. So that limits us to like 5 times 4 at most of choices. Actually, not over 2. So 10 different choices-ish. And yes, so indeed, we want to have a bigger mass difference, or at least different kind of polarization difference, so that we got a bigger dipole moment. And essentially, the only one that is bigger than what we have right now, ignoring francium, would be lithium cesium. And it has 2 issues. First of all, is lithium is just so much harder to work with. We already have difficulty working with sodium in this limit, and for some of the problem we're seeing, we have experienced cooling them down to the low temperature. It will be even worse for lithium because it's lighter, it's have unresolved excited hyperfine structure and such. And another problem is that depending on how you actually want to polarize them, which we are still working on, I guess. If you just use a static field at a given field, lithium cesium is actually have a smaller dipole moment than sodium cesium. This is because to polarize it is not only the dipole moment, the full dipole moment, molecular frame dipole moment you care about. You also care about how easy it is to align the molecule, and that is related to the moment of inertia of the molecule. And the lithium cesium just have a so much smaller moment of inertia, and so it's much harder to actually polarize if you use external field, at least.
Mm-hmm. Okay. Yeah, Matthew, if that answers your question.
Right, yeah, so it does turn out there's some optimum that you've picked here for a reason. I just didn't know what it was. Thanks.
Yeah, I wanted to add that was a really good question, and I think people are pursuing lithium cesium, so there's definitely ways that one can overcome technical limitations. So there's certainly, to me, it's just purely technical limitations. So it's a perfectly good choice as well.
Okay. All right, well, let's move on to a question from Yugal Talukdar. And he has a question about ultimately the dipole-dipole interactions between 2 molecules. It looks like he's been added to the list of people who can speak here. So Yugal, you want to go ahead and try to ask your question?
Can you hear me?
Yes.
Yeah, so my question is, once you have 2 ultra-cold polar molecules and you want to utilize the interaction between the 2 molecules, and we know that so these are like the dipole-dipole interaction, and which is going to depend on the angle between the orientations of the 2 molecules. So how are you going to control that orientation in order to have like specific interactions?
Kenneth, do you want to take that?
Sure. I mean, I can say something to that. I mean, I think it's so. First off, I guess the internuclear axis would be determined by our array. Since we're pinning down the molecules in tweezers, we can control exactly the internuclear axis between 2 molecules that we want to interact. And then you could imagine controlling the orientation. So that would be the quantization axis. I mean, if we're going to polarize them, then the electric field should also set their quantization axis. And then you can imagine possibly controlling that angle with respect to this internuclear axis how you please, I guess. Does that answer your question?
Yes, thank you.
Yeah, but maybe just to add, if I may, is that we're also interested in not having an external electric field, so the quantization axis will be magnetic field, but by preparing molecule in rotation states, rotation ground and rotation excited state, they have transition dipole moment, which is also again on the order of the same magnitude. And basically, by working with these dipole-dipole interaction in the rotating frame, we can also naturally get these large interaction. I don't know if that was clear, but feel free to chime in some more.
Okay. Yeah, if that answered the question, I think we'll move on to the next one. And also just to give people a chance to think about this as we go through the next question, the purpose of the Sternal Club as well is to get to know the panelists and their work in a variety of ways. So if you have questions about, being an experimental group at the interface between chemistry and physics and quantum, or any sort of more general questions, feel free to think of those questions as well. So yeah, I think we'll have a few more minutes of questions, move into sort of more general things, and then Stojan will give us a little more info at the end as well. So let's move on then to Noah Brayali has a question, and so we can go ahead, and Noah, you can ask your question.
Good morning. Thank you for the wonderful talk, Jessie, and thank you, Cindy, for the hosting. Can you hear me now?
Yes.
Okay, so I noticed at the end of the paper there was some discussion about percolation, and I wonder if one of the panelists can, or even Jessie, if you can comment on that connection to percolation.
Okay, so so that point is essentially like, the question is, what sort of filling fraction do we need our arrays to have to be able, for example, if we for these interactions to percolate through the whole system. And percolation theory kind of gives us bounds on, like minimum bounds on these numbers for 2D or 3D arrays. And yeah, does that answer your question, or?
So in the paper you mentioned that 50%, something about 50% was important, and I wonder if you looked at those lattices, and which lattice seemed to come to mind when you think about 50% site percolation threshold.
So for 2D geometries, I believe like triangular lattices, or yeah, like around 50 or 60% would already give, like, that's the percolation threshold.
So if we imagine a triangular lattice of these dipole molecules and they're interacting in some way, I wonder what probes you might have of the collective, the ability of the interactions to percolate. How would you know if they were percolating? Say you're on a triangular lattice at 50% filling and there's some percolation of the interaction. How would we know it?
I guess that would be if we can observe these long range interactions, I guess.
So how would I wonder what would be a good measurement observable to see that they're actually have this effectively, they're condensing and they're forming some ground state that they couldn't form if they didn't have a percolating interaction.
So I guess previously there was work done at Jila in an optical lattice, and in that case, you would observe like essentially like a coherent oscillation across the system as these dipoles are oscillating throughout. And so that would be an observable that would tell us that it's percolating.
And in the tweezer context, what would be the relevant thing?
In the tweezer context, it could be similar. Yeah, and maybe even better.
Yeah, I think that's a very good question, and we don't really study percolation theory and not know very deeply about it, but the fact that we have single particle control and single particle imaging and detections, basically we could do observable that maps to the states, and we can detect the state of the molecule, or you know, make interferometry kind of measurements. So we're not thinking about that kind of experiment specifically, but we believe the techniques that we have, if you know there are theoretical proposal and ideas of how we might measure that, we believe that we could do that. Thank you.
Okay, great. So yeah, since we got started a little past the hour, we're going to sneak into this next hour a little bit. So we'll go through one more set of physics questions. So Luke Caldwell has a question about the lifetime of the molecule. So that seems like an important thing to chat about a bit. So Luke, do you want to unmute yourself and go ahead? Let's see. Looks like we don't have him added to the list of people. Okay. Okay, so maybe maybe it looks like we're not going to have Luke face to face, but I think it's an important question, so I'll go ahead and read it off here. Could you tell us about what limits the lifetime of the molecules and whether it presents any problems to your next goals?
Sure. So I didn't go into this in the talk, but it is in our papers. So we find that the lifetime of the molecules are limited by the scattering, and we think it's coming from scattering of the tweezer light. Fortunately for us, the lifetime as is probably long enough for us to transfer to the rho vibrational ground state. So it shouldn't be too big of a problem.
Okay, yeah, so a little bit of a mystery, but maybe not quite a problem yet.
Yeah.
Okay. All right. Well, I think we're sort of heading towards the end of our time here. So let's go ahead and thank Jessie and all the panelists again for being available and the very nice work. So thank you. Okay, so I think let's see, Stojan, you want to go ahead and wrap things up and tell us a little bit more about what's ahead in this series?
Yes, thank you very much. So do you see my presentation slide?
Yes.
Yeah, okay. So first of all, I want to thank Jessie and all of the panelists for a very interesting talk and presentation of this very interesting work to us. I want to thank Cindy for wonderful moderation as well, and all of the participants for their questions in this. So before we go, I just want to let you know that tomorrow in 2 p.m., celebrating 50th anniversary of PRA, there is a conversation with Michael Fleischhauer and Misha Luking about their seminal paper published in PRA that pretty much started the research in quantum memories as we know it today. So if you are interested in that, if you're interested in Genesis, how the paper originated, how the ideas developed, please join PRA tomorrow, 2 p.m. Now, speaking of that and mentioning this 50th anniversary, I have to add as well that during this year, all of our subscription journals are offering 50% off article publication charges for any manuscript that authors wish to publish as an open access. So with that, I would like to thank everyone again on behalf of all of the organizers. And we hope and we are looking forward to our next journal club, which will happen in approximately 1 month time and will be certainly advertised. Thank you.
Thank you.
Thank you, everyone.
Thank you.
Thanks.